Today we are looking at structure 1.1, and if you haven't already done so, pause the video and download today's PDF, which can be found in the description. So this is so you can make your own notes as we go through this topic. So back to today. So in this video we will be looking at what is an element, compound and mixture, separation techniques, properties of solids, liquids and gases, and finally temperature scales. So our first point: what is an element, compound and mixture? So elements, so every element has the same proton number. They all get their own special symbol. You can think of them as grazing animals, all basically the same, like a field of cows. So they react the same, and yeah, they can be on their own or paired up as molecules. Very much like grazing animals, they're in the same, they're all the same, they're in a field, they all kind of behave in very similar ways. So let's look at a few examples. So we could have something like iron, or we could have something like magnesium or sodium. So yeah, these are all metals and these are all elements. Then we could have here something like carbon, so this is a non-metal, but a lot of the non-metals, even in their elemental form, like to be bonded together. So we've got here oxygen and hydrogen are both examples of molecules. So on to a compound. So a compound is a substance that contains two or more different elements chemically bonded in a fixed ratio. So yeah, so with compounds, the fixed ratio is really important. It can't be changed. And if you get it right, so you have to get it right when it comes to equation writing and balancing. Otherwise, when it comes to balancing, you are going to struggle. So yeah, so they're made up of atoms, molecules or ions, and yeah, the properties of the compounds are very different to the elements that make it up. So if we look at something here like water, so water is made up of oxygen and hydrogen. Yeah, the properties of water are very different to the two gases that make it up. So we've also got other compounds here like carbon dioxide and yeah, methane. So these are non-metal compounds. And then some metal compounds. We could have magnesium oxide and sodium oxide. So yeah, so these are both ionic compounds. But yeah, we can see the ratio between the two is a bit different. So magnesium oxide, it's always a 1-to-1 ratio, whereas with sodium oxide, it's always in a 2-to-1 ratio. And we'll look at why that is in future videos. But yeah, the ratios are really, really important. Okay, so before we carry on and look at mixtures, we need to talk about this idea of purity. So yeah, so both elements and compounds can be pure as long as you've only got one type of substance in your container. So if we had a container of magnesium oxide, it's going to be chemically pure. Same with water. If you had a container just with water in, it's chemically pure. And yeah, we can do the same with the elements. So container only containing oxygen is going to be chemically pure. So yeah, so a mixture is something that contains one or more substance, so your element or compound, that are not chemically bonded. So yeah, so mixtures are not pure. So different things not chemically bonded to each other would be impure. So yeah, you can separate out the mixtures via physical methods, which you can't do with compounds. So yeah, going back to the animal analogy, a mixture would be a zoo where all the animals have escaped their enclosures, and the separation techniques would be the different ways you can get the animals back behind bars, giving you the individual animals, or in chemistry terms, the pure element or compound. So looking at what this kind of look like in diagram form, so let's just get some circles drawn. So if you've got things like this, that would represent like an element. Then to make it impure, we can chuck something else in here. So this would be an impure mixture of elements. Then over here, this is currently another the same impure mixture of elements, but we can turn things into compounds. So if the circles are touching, that means there's a chemical bond, and yeah, you're more than likely to have a compound. So over here, a mixture of elements, and over here we've got a mixture of elements and compounds. Okay, so on to the separation techniques. So the main techniques are filtration, distillation, crystallization/evaporation, chromatography, and using a separating funnel. So depending on what you want to separate decides on the technique that you go for. So the first thing we're going to be looking at is an insoluble solid plus a liquid. So yeah, decanting is very basic, so that's where you have big particles of insoluble solid that will settle at the bottom of a beaker, and then you can slowly pour the liquid into another beaker. Happy days, but you won't really be doing that too much in a chemistry lab. What you'd be most likely doing is some form of filtration. So we've got either vacuum filtration, so this is vacuum filtration, or yeah, gravity filtration. So yeah, so vacuum filtration works a lot better just because a vacuum kind of helps pull everything through the filter paper. And yeah, how does it work? So it works based on the size of the particles. So insoluble large solid particles, you could imagine them to be an elephant, and the liquid with much smaller particles could be a cute little warthog. So, and your job working at the zoo is to separate out these two. So if you herded both of these animals towards some bars, then the warthogs will be able to fit through and the elephants not. So how does that work with filtration? So yeah, you'd end up with the large solid particles on your filter paper, and your liquid would be able to pass through, and then you've got that at the bottom of your conical flask. So there we go, that's how we can separate out those two. But imagine we have a soluble solid plus a liquid. So there's two techniques you can use here. So we could do evaporating or crystallization, so they're very, very similar. So with this, you evaporate the liquid to dryness. So once you've evaporated to dryness, you are left with, for a pen, you're left with your solid particles at the bottom. So yeah, so how is it different? So with evaporating, you'd end up, you've got your solution, and you just let evaporation do its thing, and you will end up with your solid without the liquid. With crystallization, the only difference is that you heat your liquid for a bit to give yourself a more concentrated solution. So yeah, it's a more concentrated solution, and then you let evaporation do the rest, and then again you're left with your solid crystals. Happy days. So with simple distillation, you get both the solvent and the solute. So solvent, just a fancy word for liquid, and a solute is a fancy word for the solid. So your liquid would end up over here, and your solid would stay over here. So taking this back to the zoo, if you want to keep both the hippo and the birds, then you would use simple distillation. So the hippo is representing the solid, the birds representing the liquid. But if you don't want to keep your birds, then you do the evaporation method. If you do want to keep the birds, then you do the simple distillation method. So with this, so you can imagine you heating it up, the birds fly away, and then you can catch them in some kind of net, and then you've kept both the birds and the hippos. So with the insoluble solid plus soluble solid, you do a combination of these two techniques. So what you would first of all do is you would get a beaker, dissolve your soluble solid, then you'll do some filtrating, and you'll be left with your insoluble solid on the filter paper. Then you've got your soluble solid in a solution over here. So then to get the solid on its own, you can do the evaporation or the crystallization technique to be left with just your solid. Okay, so moving on to liquids now. So we've got two techniques. So we've got immiscible liquids, and which uses a separating funnel, or we've got the miscible liquids, which uses fractional distillation. So you can imagine the immiscible liquids as different fish who don't get on. So you drain half the tank, and the more dense fish would be at the bottom. So let's look at that in terms of chemistry terms. So yeah, once you've got your separating funnel set up, it will kind of look a bit like this. And your more dense solution, so this is always going to be like an aqueous-based solution, so a water-based solution will be at the bottom. And then, yeah, so we've got the water aqueous-based solution at the bottom. Then you'd have the organic layer on top, so this could be oil, or it could be any of the organic solvents would be on the top. And then, yeah, what you do is you just drain it, so your aqueous layer is now collected in a beaker, and you are left with your organic layer in the separating funnel. All right, so now onto fractional distillation. So with the miscible liquids, so the liquids are mixed together. So we could imagine that these are two different types of fish that are okay with each other. They're fully mixed, they're great friends. But the smaller fish hate hot water. So when you heat the bottom of the small fish, which would represent a liquid with a lowering boiling point, moves up through the condenser, up through the fractionating column, and then through the condenser. So going back to talk about it in terms of chemistry, so you'd end up with the lower boiling point liquid would be over here after it's moved through the fractionating column, and then it gets condensed by the condenser, so you're going from a gas back to a liquid. And then your liquid with a higher boiling point would stay over there. Happy days. All right, so now on to kinetic theory, so the properties of solids, liquids, and gases. So a solid has a fixed shape and volume, particles can't flow or be compressed, they have regular arrangements, and have strong forces of attraction holding them in place. So basically the same as a tortoise. So a tortoise could represent a solid as they move very slowly, remembering that particles are always moving, even when it gets very cold, and yet their hard shell could represent the solid's fixed shape. So I'm sure you can remember doing these diagrams back at school, where you very quickly draw some circles. So we've got the regular arrangement of particles, and then we can add some little lines to show that they are vibrating, but you're vibrating in a fixed position. Right, so moving on to a liquid. So liquids have a fixed volume, but they fill their containers. Particles can flow, but can't be compressed. They have no regular arrangement, but they do have attractive forces that hold the particles together. So just like an octopus in some ways. So your octopus could be a liquid if you squint your eyes a bit, because they can change their shape to fill a container. They can also sort of flow as they move through the ocean, maybe. So looking at the particle diagram, so again, doing some lovely neat circles, and they're all pretty much touching, but no regular arrangement. Okay, so on to gases. So no fixed volume or shape, they expand to fill the container, and your particles move quickly and readily diffuse. Highly compressible, and the particles have almost no forces of attraction. So just like a hummingbird. So hummingbirds can fly, pretty much the same as a gas. You could even compress their space if you were feeling mean, but I wouldn't recommend doing that. So obviously there are some limitations to these models, but before we talk about that, we can just draw our gas in. So our gas is free to move. So obviously there are some limitations to this model, as well as some of all the other animal analogies I've used so far. But the point of them is to help you remember what's going on, as the sillier something is, the easier it is to remember. So let me know in the comments the strengths and limitations of any of the models I've used in this video. I would love to hear your thoughts. Okay, so on to almost the final thing, so change of state. So energy is transferred during a phase change. So red, all the red words here are for when you are applying heat energy, and blue are for when you are taking the energy away. And then remembering at a phase change, so here's our phase change graph. So remembering at a phase change, energy is also needed, so either given out or taken in, because phase changes all requiring like a swap of energy. So this is why you are getting the flat lines during this heating graph. And what else do these flat lines tell you? So if they're perfectly flat, like they are in my diagram, then it means you have a pure substance. Okay, on to the final thing. So temperature scales. So temperature is a measure of thermal energy. How quickly the particles are moving, is how much kinetic energy they have. So it's always good to think about temperature like this, and not just about something being hot or cold. You need to be thinking about it in terms of kinetic energy. So yes, faster moving particles can react quicker, and they also take up more space. So as we can see here, so this is like a model representing a thermometer. So when you heat up the particles, because they then have more kinetic energy, they move around more, then they take up more space. Right, so just to find a few things with the temperature scale. So the absolute temperature scale is measured in Kelvin. So the absolute scale is measured in Kelvin. And you need to be able to convert between the two. So 0 Kelvin, so that's absolute 0. So that means particles have no kinetic energy. So so absolute 0 Kelvin is minus 273.15 degrees Celsius. And you need to be able to convert between the two scales. And luckily it's nice and easy, because 1 degree Kelvin is the same as 1 degrees Celsius. Happy days. Right, so there we go. That's everything from me. So thank you for watching. And if you want up-to-date new syllabus IB chemistry videos, then please do subscribe. Or if you want extra help via one-to-one tutoring, then check out my website, link in the description, or email me directly at contact@argontutor.com. All right, so thank you again, and I will catch you in the next one. Bye.